So now let's talk about the final and most serious problem, which is that stuff in the internet, nodes, links, etc., is failing all the time. And while it's true that we just argued that the asynchronous Bellman-Ford shortest path routing protocol is guaranteed to converge to correct shortest paths, that was assuming that the network was static, that no links were coming up and down. So one particularly simple problem in the presence of failures is what's known as the counting to infinity problem. So I'm going to show you a particularly contrived version of this problem just to kind of illustrate the point in the simplest way, but it's quite easy to come up with more realistic examples. And this problem is not just some kind of theoretical flaw in the distributed Bellman-Ford algorithm. This problem really was observed in practice with those routing protocols from the 1970s. So imagine we just have a super simple network, vertices S, V, and T, bidirected arcs from S to V and an arc from V to T. Everything has unit cost, and we're doing routing to the destination T. You might, if you want a more realistic example, think about the arcs between S and V as standing in for longer paths that have multiple hops. In any case, let's imagine that we successfully computed shortest paths on this basic network. So the distance from T to itself is 0, from V to T is 1, and from S to T is 2. Now again, the issue is that links are failing all the time in the internet. So at some point, this link from V to T might go down. So at some point, V is going to notice that its link to T has failed, and it's going to have to reset its shortest path estimate to T to be plus infinity. And in an effort to recover connectivity to T, it makes sense for V to ask its neighbors, do they have paths to T? And if so, how long are they? So in particular, V will poll S, and S will say, oh yeah, I have a path to T of distance only 2. And V says, oh, well, that's great. Currently, my estimate to T is plus infinity. I can get to S with length 1. S says it can get back to T with length 2. So that gives me a path of length 3 to T. Now, of course, the flaw in this reasoning is that S was depending on V to get to T. And now all of a sudden, V circularly is going to use S in its mind to get all the way back to T. So this already illustrates the dangers of naively implementing the asynchronous Bellman-Ford algorithm in the presence of link failures. Where does the name counting to infinity come from? Well, you can imagine that for some implementations of this protocol, S would then say, oh boy, okay, V just revised its shortest path estimate to T to be 3. My next hop was to V, so if V takes 2 longer to get to T, then I'm going to take 2 longer to get to T as well. So at that point, S updates its shortest path distance to be 4. And now this keeps going on. At this point, V says, oh, well, if S is going to take 2 longer to get to T, I was depending on S, so I have to go up by 2, and then S goes up by 2, and V goes up by 2, and so on forevermore. So failures cause problems for the convergence of distributed shortest path routing protocols. Not just the counting to infinity problem, there are others as well. And this is a tough issue. Much blood and ink has been spilled over the relative merits of different possible solutions for dealing with failures. Back in the 1980s, people were largely proposing sort of hacks to the basic protocol. I will give them credit. They had some pretty ridiculous and fun names for their hacks, like Split Horizon with Poison Reverse. But what eventually people converged on is moving from these so-called distance vector protocols to what are called path vector protocols. And what happens in a path vector protocol is each vertex maintains not just the next hop to every possible destination, but they actually keep locally the entire path which is going to get used from V to each destination T. So there's definitely some irony here, because this is essentially the solution to reconstructing optimal solutions in dynamic programming that we've been studiously avoiding this whole time. You might recall when we first started discussing reconstruction algorithms, this was back independent sets of path graphs, we first said, well, you know, you could, in the forward pass through the array, store not just the optimal solution value, but the optimal solution itself. But we argued, well, that's not really the best idea. It wastes time, it wastes space. Much smarter is to just reconstruct an optimal solution by a backward pass through the filled-in table. But what's happening here is this optimized version of the reconstruction algorithm that doesn't use extra time or space is just not robust enough to withstand the vagaries of internet routing. So we are going to the cruder solution where we literally just store optimal solutions, not just the solution value itself. So that explains why this is called a path vector protocol, right? Distance vector protocol, you store the distance for each possible destination. Here we're actually storing a path for each possible destination. So the drawback is exactly what we've been saying all along. If you store the optimal solutions and not just the optimal solution value, it's going to take quite a bit more space. And indeed, doing this blows up the routing tables in routers. That's just a fact. There are two quite important benefits. The first we've already discussed, you're more robust to failures. I'm not going to discuss the details about how you use this extra path information to handle failures better, but certainly in our contrived motivating example, you can see how if S and V actually knew the entire path they were storing to T, they could make sure that they didn't get into this counting to infinity problem. But moving to a path vector protocol doesn't just add robustness, it also enables new functionality. So in particular, passing around entire paths allows vertices to express more complicated preferences over routes than merely what their lengths are. Imagine, for example, you're a small internet service provider and you have a much more favorable contract with AT&T than you do with Sprint. So it costs you much less money to send traffic through AT&T as an intermediary than it does through Sprint. Well, now imagine you're running this distributed shortest path protocol, and two of your neighbors offer you two paths to get to some destination T. The first path goes through AT&T, the second path goes through Sprint. And of course, the only reason you know this information is because it's a path vector protocol and you're passing around the actual path and you can see what the intermediate stops are. Well, then you're free to say, oh, well, I'm going to use as my path to T, and this is what I'm going to advertise to other people. I'm going to advertise and store the path that goes through AT&T. I'm going to ignore the one that goes through Sprint. So that is more or less how the Border Gateway Protocol, aka the BGP protocol, works, and that is the protocol which governs how traffic gets routed through the core of the internet. So that wraps up our discussion of how shortest path algorithms dating back to the 1950s has played a fundamental role in how shortest path routing has evolved in the internet over the past half century.